everyone. I'm Raffaella Villa, Business Development Engineer for Compounding at MCM Angst+Pfister Group, and I will give you today a presentation on elastomer sealing for hydrogen applications. I will go through a short introduction and then describe the testing plan and results we had on our elastomeric sealing design for gaseous hydrogen application, together with a case study, and then I will conclude with some remarks on our findings. So, as you know, nowadays hydrogen is becoming more and more important as a possible energy source and energy carrier. Throughout the life cycle of hydrogen, from the production to the storage to the usage, sealing may be used in different kind of steps. In all the steps, sealing in hydrogen application will require to fulfill very challenging requirements. First of all, extreme temperature ranges, high pressures up to 1000 bars, permeation to the hydrogen itself, so the sealing capability of the specific material will need to be considered, and then tight sealing requirements because hydrogen has a very broad flammability range in air. Elastomeric sealing are meant for gaseous hydrogen application. Cryogenic application are out of the scope for elastomeric sealing. And we did our work first focusing on high hardness compounds for high pressure applications, working on fluoroelastomers, hydrogenated nitrile rubber, and EPDM. And then we did some work also on standard 70 Shorey compounds, still to investigate possible low pressure applications. So, what we did on these high hardness compounds, so 90 Shorey compounds, was to evaluate some key properties that we believe needs to be considered when working with gases at high pressures. First of all, permeation to gases. Permeation, when you have a gas in contact with an elastomer, this is a key parameter to be considered. Permeation is the product of solubility and diffusion, basically, and will depend on many factors. First of all, temperature and pressure, then thickness and surface area of the material exposed to the gas itself. Polymer type and compound formulation will play a role. And then gas type. Of course, different molecules will have different sizes and will have also different compatibility with the materials they are in contact with. In this case, we did test permeation according to ISO 27821 in order to evaluate our product portfolio and the effect of the different polymers and different formulation types on the permeation to hydrogen. At the same time, we did run some leakage tests. Leakage may occur in two ways, basically. One is the permeation through the sealing material. The other one is the leak path between the sealing material and the counter surface. In this case, the test method used was an internal method where we did measure leakage of hydrogen on O-rings settled in a pressurized vessel at a specific temperature and pressure. Last but not least, on some specific materials, we decided to run also some rapid gas decompression testing according to NORSOC standard M710. Rapid gas decompression is an important issue to be considered when talking about elastomers in contact with gases. Gases at high pressure can permeate into the elastomer, and when the pressure is suddenly released, you can have this gas escaping the material. The gas can escape without any damage, but it can also give big damages like blister, voids, cracks that will then lead to seal failure, basically. So this is the main test we have started to do, all performed at 100 degrees C, 150 bars in pure hydrogen. As said, we did start on 90 Sure compounds. We did focus on 2 different HNBR compounds based on 2 different HNBR grades, 2 different FKM compounds, also based on different FKM grades, and 1 EPDM compound. On all of them, we did permeation test and leak test in pure hydrogen, 100 degrees C, 150 bar, and on selected materials, we did run rapid gas decompression tests at different pressures. So what you can see here in this slide and in the chart is the results of the permeation coefficient for the different materials that we have worked on. They will behave different, and as expected, permeation is influenced by the polymer type and by the compound formulation. In fact, you can see that there are different results or different permeation coefficient even within the same family of polymers, the HNBRs and the FKMs, for example. Permeation coefficients are quite low in general, as the solubility is very low. In fact, what we could infer analyzing the data is that hydrogen permeation seems to be dictated by diffusion, which is kind of very fast into the material due to the low molecular size of hydrogen. And but then hydrogen is not really dissolved in the material, so very little is dissolved there. In contrast, for example, with CO2, where you have significant amounts of CO2 usually dissolving into different elastomers. So in general, the observation is therefore that hydrogen is diffusing very fast in and out the material, but is not remaining absorbed on that, so solubility is quite low. The leak test that was conducted in the same conditions in parallel showed basically the same trend as for these permeation coefficients. So basically, the materials with lower permeation coefficient were the ones leaking less. This means that, or this suggests that the predominant reasons for the gas for the leakage was permeation, so natural leakage. On selected materials, we then ran some rapid gas decompression testing at different pressures, HNBR and FKM, with very good results in general, thus meaning that suggesting that possibly rapid gas decompression may not be a big issue in case of hydrogen gas, in contrast with other kind of gases. And this is possibly due to the fact that, as said before, diffusion is very high, so the hydrogen passes through very easily, but then solubility is very low, so no or little hydrogen is retained on the surface or in the material itself. So on 70 Sure compounds, we also did run some permeation testing. In this case, we used a different standard, so ISO 15105, as for the VGV certification process 5101. In this case, the test is made at room pressure and temperature, and once again, working on different polymers, FKM, EPDMs, HNBRs, what we could find is that the polymer type and formulation are influencing the result, and you can see differences within the same family of polymers, basically. Afterwards, together with a customer of ours, Galperti, that I would like to thank for the great collaboration, we did run some kind of case study to assess the orange performance with forming gas. In this case, we did study the best performing material in terms of permeation coefficient, so HNBR and FKM, in a modular double block and bleed valve. So the scope of the work was to evaluate the sealing capability of the O-rings in different conditions. So we did analyze the sealing capability for static seals, dynamic seals, after long exposure period. So we did run a 1 week test under pressure, and then sealing capability after valve endurance test, so after dynamic operation. This kind of test was was done at room temperature with a pressure ranging from 0 to 425 bars. On informing gas, 95% nitrogen, 5% hydrogen, on HNBR and FKM, or in different different positions with different cross sections and different diameters. Detection was made by hydrogen flow using a mass spectrometer with the sniffing method. Here you can see the sketch of the valve, or the double block and bleed valve, where we had mounted O-rings of FKM on the left side, valve AB, and HNBR on the right side, valve CD. O-ring, as said, was different in different position with static and dynamic operation. In this chart, I have summarized the different steps of the testing, where we did all the testing at room temperature and with varying time lengths and pressures. Basically, it was started with an hydrostatic body test, followed by different seat leak tests at different pressures. In particular, we had some fugitive emission and leak path tests at different pressure, 6 bars, 50 bars, 150, 255, and 425 bars. Followed by 7 days at 425 bars, where the leakage was detected every 24 hours. After that, fugitive emission and gas leak test was made again at 6 bar and 425. Then the valve was operated dynamically 200 times, a full operation. And then once again, the test was made, the fugitive emission and leak test was made again. In no cases we had leakage, thus showing that the O-rings were basically sealing properly. In general, when we dismounted the valve, we have analyzed the O-ring that didn't appear damaged in any case. No significant deformation was reported, and compression set was tested on some of the O-rings, giving values that are in accordance with the nominal values. Some of the O-rings were also cut in 4 parts, and the internal surface was analyzed and magnified, showing an homogeneous surface, no cracks, no blisters. So basically, no leakage was detected on the different O-ring paths. The sealing performance were then therefore confirmed. Given the values that we have obtained for permeation at 100 degrees C, we may have expected some leakage at some point, but in this case it didn't happen. On one side, because probably temperature is, of course, lower in this case. We did run the testing at the room temperature, and also because the geometry is completely different. In general, there's the possibility to, in the future, to run tests at higher temperature to prove this kind of testing. So, in general, what we did was to evaluate for our sealing materials permeation, leakage, and RGD properties. Permeation seems to be dictated by diffusion, as solubility seems to be very low. The permeation coefficient in some way allowed us, in accordance with theory, to rank our compounds in terms of polymer type and formulation. And I didn't report the details here, but we did run also testing in parallel on helium for permeation and leakage to show that the order of magnitudes were similar for the permeation coefficients. Rapid gas decompression events seems to be possibly not an issue in the case of hydrogen for standard RGD proven materials. And we are now in the phase of testing aging in hydrogen for the same kind of materials that we have analyzed so far. So thanks for your attention. This is the end of my presentation. Thank you.